Hello there. We are in the ninth lecture now, and this is the final lecture for the second theme that we are studying. So let me start sharing my slides, and we will soon see some of the important and nice things. Before we go on to studying the further things, I have to announce one correction. So if you remember, in the third lecture, we did an example of a computation using two-digit arithmetic. It was for this particular function, which is a polynomial, actually, x cube plus x square plus x plus 1. And I wanted it to be done at x equal to 1.876. Okay, so I wanted it to be done using two-digit arithmetic, but what we actually did was this. I said this was two-digit chopping and this was a two-digit rounding, but note that we are actually using three digits here, 187. So if we write it correctly as we should, it will be 0.187 into 10. And then we see that there are in fact three digits. So this is not two-digit arithmetic, it's actually three-digit arithmetic. And so I should change, instead of changing the computations, I will simply change the word here and I'll say that we are doing three-digit arithmetic. In fact, when we computed fx, we were looking at four digits. Even that's not allowed. We should look at only three digits there. So that change would be 12.8 and 13. If you remember, it was 13.05. And so now it has simply become 13. So this is the correct three-digit chopping and three-digit rounding method. And we will also modify these numbers and write them in the form that we have learned writing, and that will then reduce the confusion to some length. So we will write, remember this is 1.87 with the chopping and 1.88 with the rounding. So that will become 0.187 and 0.188. The next two numbers, which are x square with the chopping and rounding methods, which were 3.49 and 3.53, they will become 0.349 into 10, 0.353 into 10. And finally, we will have 0.652, 0.664, and the final answer will be 0.128 into 10 square and 0.13 into 10 square. In fact, once we have done this, we will also need to compute the absolute error and relative error afresh. So I am very sorry if this has resulted in some confusion, and I would like to thank the TA Shreya for pointing it out to me. All right, so thanks a lot for this, and once this is taken care of, we return to the method at our current interest, which is the order of the fixed point iteration method. So what we have done is that we had fixed the notion of order of convergence of a sequence, and the fixed point iteration method gives us a sequence which converges to the root that we are looking at. So if you are looking at this function gx and you are looking at the root of the equation gx equal to 0, suppose x equal to p is the solution. So this is the problem that we have, and we are trying to find methods to find this root p with the best possible accuracy that we can. Suppose we convert it into a fixed point problem using another function fx. Okay, then whenever the derivative of f at p is non-zero, we get that the fixed point iteration method is linear. Remember, gx equal to 0 is a fixed function. That's a fixed equation. We want to find root of this equation, and there are many ways to convert it into fixed point iteration methods. So if we take one of them, which is fx, which has the property that for that fixed point iteration function f, the derivative at p is non-zero, then the corresponding fixed point iteration method gives you only linear convergence. Whereas we also had this result in the last lecture that whenever the derivative of this fixed point iteration method function is 0 at p, then we get at least a quadratic order of convergence. So we should try to look for such a fixed point iteration function whose derivative is 0 at p. And we saw that Newton-Raphson method was one such function, provided the p is a simple 0 of the function g. Now, if p is not a simple 0 of the function g, then Newton-Raphson may not give quadratic convergence. We saw an example for this as well. And so it's a natural thing to wonder whether we can modify the Newton-Raphson method, which has worked so well for functions with simple 0. Can we modify it slightly and get some method which will work for any function, no matter what the order of 0 is, what the multiplicity of 0 is? And I had said in the last lecture that you bet mathematicians will find an answer to this, and here is an answer. We will modify the Newton-Raphson method in a slightly different way using theoretical framework. So let me just repeat what we say about the multiplicity. Whenever we have this function g from ab to r, and suppose x equal to p is a root, that means it's a solution to gx equal to 0. Then we define this new function, which is gx upon g prime x. Gx divided by g prime x. It's a new function, and what does it do? So if you have that the multiplicity of x as a 0 of g, or which is also called the order of x equal to p as a 0 of g, is m, then gx will be x minus p power m into qx, and this qx has the property that it is not 0 at p. Okay, the 0 contribution at p is taken and consolidated in this x minus p power m. Q has no 0 at p. Then compute the derivative, which will be m x minus p power m minus 1 into qx plus x minus p power m into q prime x, our usual formula for derivative. And now we write this function mu x. So mu x is then going to be, see, the x minus p power m factor occurs in gx, which is the denominator for mu. And in the numerator, you have x minus p minus m minus 1, x minus p power m minus 1 for the first one. And for the second part, it is the x minus p power m. So you can take x minus p power m minus 1 common from the denominator, and there is x minus p power m in the numerator, and cancelling those two out, we get mu x equal to x minus p into this another function whose numerator is qx, and therefore this another function is not 0 now at p. So we have converted our function, earlier function g, into another function for which x equal to p is a simple 0. Okay, and moreover, when you have that q is not 0 at p, remember we have written gx equal to x minus p power n into qx, and q is not 0 at p. We will of course assume all the nice conditions for our functions g and q and so on. So we will assume that q is continuous. Now whenever q is continuous and it is not 0 at a point, then there must be some small interval around that point such that q is non-zero on this whole interval. So therefore gx has no other 0 in the neighborhood of x equal to p, because you have written gx as x minus p power m into qx, and in that interval around p, q has no 0. So gx cannot have any other 0 than p, and therefore mu will also not have any other 0 in that neighborhood. So whenever you are approaching a 0 of mu, it will have to be p, and therefore that will give you the original 0 of g that you were looking for. Okay, so whenever now we convert this root finding problem for mu x equal to 0 into a fixed point iteration problem, then it will give you some 0 of mu in some neighborhood of p, but that has to be p. It cannot be anything else. Okay, that is understood. So we now apply Newton-Raphson method to mu x. Okay, remember mu x is gx upon g prime x. So this fixed point iteration, we are defining a new one. It will be given by fx equal to x minus mu upon mu prime, where our mu is already g upon g prime. So it will be x minus mu is g upon g prime, and we have to compute the derivative of g upon g prime. which you know it's the numerator upon denominator whole derivative is numerator derivative minus into denominator minus numerator into denominator derivative, and then the whole thing is divided by the denominator square. So that's the formula we will have, and then this g prime x whole square, which occurs in the denominator of the denominator, will go to the numerator. It will cancel that one g prime which is there in the denominator of the numerator, and it simplifies, if you can call this as simplification, to this x minus g prime upon g prime square minus g double prime. This is the formula that we get. This is the slight modified Newton-Raphson method. Okay, so this iteration will now converge to P with at least a quadratic order of convergence. Why? Because mu is a function which has P as a simple zero, and then we are applying the Newton-Raphson method to such a function, and therefore we are going to get this fixed point iteration method which will converge to the point P with at least the quadratic order of convergence. However, whenever we are trying to look for something better, whenever we are trying to do better even in situations which don't look good, which is like the situation where we had that x equal to p had a higher multiplicity of 0, then there are also some problems. So there are two drawbacks with this method. The theoretical drawback is that you have to do more computations, because you now need to compute g double prime also. In addition to computing g and g prime, we have to also compute g double prime. So I leave it to you as a homework to see what second method will do to the function mu. Of course, we will have to compute g prime in some way, but how the second method will work and whether it will reduce the computations, theoretically at least, that is something that you should try to find out. There is also computational drawback here. If you look at this denominator involves g into g double prime being subtracted from g prime square. Now we are assuming that our point P is a 0 of g with higher multiplicity, which means that P is a 0 of g and P is also a 0 of g prime. So near P, we are cancelling two terms which are almost equal. So that's a computational drawback. And this computational drawback will result in it will give some effect on the order of convergence for this modified Newton-Raphson method. So if you remember, we had considered this function and we wanted to find its root at x equal to 0. That's a root of multiplicity 2, and we found that our Newton-Raphson did not give us a quadratic convergence. But we will look at the Newton-Raphson method, and Newton-Raphson method gives P1, which is P0 minus g prime upon g prime square minus g double prime, to be 1 minus, you just put the values of gx, g prime x, which will be e power x minus 1, and g double prime x, which is just e power x, at x equal to 1. Our P0 is 1. And this gives you minus 2.3421061 into 10 power minus 1. So this is closer to 0 than the first term for Newton-Raphson, if you remember, which was 0.58918. Okay, so the modified Newton-Raphson method is giving you better results. In fact, we have the whole table. The left-hand side table, which gives you the 8 terms, that was the Newton-Raphson method, and we saw that it was not converging to the point 0 as well as we would have liked. Whereas this modified Newton-Raphson method does converge to 0 considerably faster, and that's why the modified Newton-Raphson method is better. We see that from 4th iteration to the 5th iteration, or even the last 3, we see that there is no much improvement, but that is because we are cancelling almost equal terms in the denominator of the fixed point iteration function. So that's a small drawback, but it will still give you better convergence than the Newton-Raphson method will give. Okay, so of course you may ask, what would happen if you are taking a simple 0 and without thinking much you just apply the modified Newton-Raphson? Meaning, why worry about whether x equal to p is a simple 0 or not? Why don't we always work with the modified Newton-Raphson? That could work. Why not? In fact, if you remember, we had considered this example some lectures back, and we had this was the 1.365230001. We were trying to converge to this, and we had at least 5 different fixed point iteration methods for this function. But the Newton-Raphson among them gave us this, whereas the modified Newton-Raphson will be this thing. It looks complicated, but once you encode it into a computer, then computer will take care of the further calculations. So only care that you have to take is while in giving the input to the computer. If we now look at the initial approximation P0 equal to 1, then our Newton-Raphson method gave us these 3 values. Whereas modified Newton-Raphson gives almost the similar values. It may seem that P1 is closer to the intended route that we had, but by the third method, the Newton-Raphson, by the third iteration, Newton-Raphson method also has caught up with the modified Newton-Raphson method. So, excuse me. So, although the modified Newton-Raphson method is not working significantly better, both are working fine. Of course, the second method will require substantially more calculations because you will need to compute G double prime, and then the formula is slightly more complicated. So this is what we have for modified Newton-Raphson method. So we have learned so many methods by now, and you might wonder whether there are any more methods that we need to learn. You know, this is what happens when we do too many things, and at the end the student may just get bored and he say, are we really done, or do we have to do some more things? Are there some more things which are left? So maybe there is one more thing which I could give you just to give you an example of how people work in different directions. So there are in fact many methods that one can think about. We will not be able to learn all of them. When you go and do research, what you will have to do is that you will have to look at some reference books, see what are all the methods, and apply the one that seems to be the best one. But here is one method which improves the order of convergence. So you might have a sequence which converges with some order. From the same sequence, we can construct another sequence which converges with a better order of convergence. So suppose I have a sequence Pn which converges to P linearly. The order of convergence here is linear. Okay. Then for large enough n, what we will have is that Pn plus 1, Pn, Pn plus 1 and Pn plus 2. These will be very close to P. For large enough n, you know, the sequence converges to P means that for any epsilon positive, there is some capital N such that the Pn's for n bigger than or equal to that capital N will be in the epsilon neighborhood of P. So any two Pn's or Pn and Pm are going to be very close to each other. That is the Cauchy condition. So we will have actually that happens for any m and n after that big N. Okay. So you will look at Pn, you will look at Pn plus 1, and then the next one, Pn plus 2. So these three are all very close to each other, which means that their distances from P are roughly the same. Approximately Pn minus P, Pn plus 1 minus P, and Pn plus 2 minus P, these are all the same. And we are also assuming that there is no sign conflict. We assume that they are on the same side of P. So that if Pn minus P is positive, we assume that the others are also positive, so that we don't have to take modulus here. Okay. So for such a large enough n, the square of the middle term will be approximately equal to the product of the other two terms. So Pn plus 1 minus P whole square is approximately Pn minus P into Pn plus 2 minus P. And then you can expand this out nicely. Pn plus 1 minus P whole square, you apply the binomial theorem, then you take the product on the right hand side and do some simplifications, which will give you that P is approximately Pn minus Pn plus 1 minus Pn whole square upon Pn plus 2 minus 2 Pn plus 1 plus Pn. So here we started with Pn converging to P linearly, and now we have some another term which changes for each n. So it's a term which depends on n. We will call it Pn hat or P hat n. So this P hat n is the term which is also going to converge to Pn, because the thing on the right hand side is going to be 0. So the limit of P hat n is same as the limit of Pn. And this is the new term which will give you a better order of convergence. This is called Aitken's delta square method of convergence. Why delta square? Because delta of the sequence Pn is Pn plus 1 minus Pn. Delta Pn is Pn plus 1 minus Pn. Delta typically stands for difference. So here we have the difference delta of Pn, which is the Pn plus 1 minus Pn. So our numerator is delta of Pn whole square. And the denominator is the delta of delta. So remember, what is delta of Pn? It is Pn plus 1 minus Pn. And delta of Pn plus 1 is Pn plus 2 minus Pn plus 1. And then the delta of delta Pn, that would have to be delta of Pn plus 1 minus delta of Pn, and there that's what we have in the denominator, which is the delta of Pn plus 1, which is Pn plus 2 minus Pn, and then you subtract the next delta, which is Pn plus 1 minus Pn. So Pn plus 2 minus Pn plus 1 minus Pn plus 1 minus Pn, which gives you Pn plus 2 minus 2Pn plus 1 plus Pn. This is the Aitken's delta square method of accelerating convergence. So we consider this sequence Pn, which is cos 1 upon n. As n goes to infinity, 1 upon n goes to 0, but cos 1 upon n goes to 0 very slowly. Cos 1 upon n will go to 1 very slowly. It's a linear convergence, and we apply the Aitken's delta square method to this and note the results in the following table, and we see immediately that from P hat 1 we are getting very close to 1. So our P1 was cos of 1, that was just 0.54030, but P hat 1 is 0.96178, which is almost close to the thing. The very first digit is correct from the very first approximation. And by the third or fourth approximation, in fact, the third approximation also, if you apply the rounding method, we are correct with the second digit. And there, this is the way we are going to get this nice sequence of points, which is converging to 1 with a higher order of convergence. Okay, so this Aitken's delta square method is a very important method, and we will try to see some examples of that in the tutorial also. But that is all for our this theme. So we have completed the second theme of our course, which is the equations in one variable, and we will now start looking at the third theme, which is the interpolation. So that's also a very, very important theme, and we will have a few more lectures on this. And after that, we will go into some real numerical analysis. So hang on with this course. It's going to get more and more interesting, and I hope you will stay tuned to the course. Thank you.